A lens is a focal length of 5 meters, and the distance of the object is 2 meters from the center of the lens. A. If the lens is a thin converging lens, find the magnification. B. If the lens is a diverging lens, draw where the image would be. And C. Find the power of the lens. So we're going to do part A first. So before I draw a diagram explaining what this means for part A, I'm going to find the magnification. We could do that using this equation. 1 over the focal length equals 1 over the distance of the image from the center plus 1 over the distance of the object from the center. Since we have the focal length and the distance of the object from the center, we could just solve for di. It's going to be 1 over 5 meters minus 1 over 2 meters. That will equal, plug it into my calculator. Equals negative 0.33 meters, or roughly 3 meters. Okay, so now we use our equation for magnification. The height of an image over the height of the object, or the negative of the distance of the image from the center over the distance of the object from the center, equals the magnification. If we plug our number in, we get negative 3 meters over the distance of the object, 2 meters. So this is going to be dimensionless. We get 1.5. So this means the image is actually bigger than the object, and it's positive. So what do we do with this information? Well, let's draw our diagram. So this is our converging lens, or our convex lens. We're going to draw our principal axis, EA. We're going to draw the center line. It goes across the center point. We're going to draw the height of the object. And what this magnification tells us is actually that the image will be on this side of the principal axis instead of this side, and it'll be on this side of the principal axis instead of this side. And that's because when the image is on this side, it would be inverted, meaning the magnification would be negative, but we see that it's positive. Right. So I will draw a parallel ray that, due to refraction, will then refract downwards. There'll be a change in slope there. This right here will be the focal length, which is the length of the center to the focal point. This is DO, by the way. And And then we can actually trace this line backwards. Let's try this. Trace that line backwards. And we're actually going to wait for that. We're going to want to see where that intersects with another ray. This ray that passes across the center. Let's take out this line. Let's say they meet right here for space's sake. But this would be the intersection. But we're just gonna say they intersect right there. We'll draw a line. And this would be HI. Hello. And then this would be DI. Now visually, the focal length looks a lot smaller than the DI. That's just because of human error in drawing this diagram. But the focal length in this problem is actually larger than the distance of the image from the center. So now I'm going to draw our diverging lens. And a converging lens is often called a convex lens. A diverging lens is also often called a concave lens, and you'll see why. So as you can see, there's a concavity with this lens. Oops. We have our principal axis. We have our line across the center. We have our object. And we also have this parallel ray. This parallel ray is actually going to go up. And you also have another parallel ray, or not parallel ray, another ray. This goes through the, oops, say it goes through the center. Try this again. Goes through the center. Okay. Now with this, you're actually going to trace back this ray that goes through the diverging lens. Again, this is our focal point. And at this intersection is actually the image. So we can go ahead and label our diagram accordingly. This, oops, be the, let me label this differently. Okay, now for part C, we need to find the power of the lens. So the formula for power is simply 1 over the focal length. We know the focal length for this problem is 5 meters, so we can just write 1 over 5 meters, and that will equal 0.2 0.2, and then our units, which is the inverse of meters. Thank you for watching.